In this video, we'll look at electronegativity and ionic bonding. We remember in our last video, we really focused on covalent bonding and the sharing of electrons. Here we're going to look briefly at ionic bonding and how the electronegativity can play a role in that. If we remember electronegativity, anything with an electronegativity difference of 2.0 or greater, we consider that ionic. And looking at our trends for electronegativity, our metals down here, you can see they have very low electronegativity numbers versus the nonmetals. So most of the metals, even our transition metals, fall kind of around 2. And then it's only once we get to the alkaline metals and the alkaline earth metals that we really get below 2. So generally between 1.5 and 2, that's where we find our metals. And we can use these electronegativities to assign oxidation numbers. So when we're using them to assign oxidation numbers, the more electronegative atom is assigned all the shared electrons. The less electronegative atom is assigned none of the shared electrons. When each of the atoms is in a bond, it's assigned all of its unshared electrons. So our oxidation number will equal our number of valence electrons minus the number of shared electrons and the number of unshared electrons. So this is one other way we can figure out our oxidation numbers, is by looking at the electronegativity and looking at which electrons are shared and which ones are unshared. And then when we look at ionic bonding and electronegativity, the larger the electronegativity difference means that the electron is actually transferred completely. So when this happens, the two ions remain bound by electrostatic attraction. So positive charge gets attracted to a negative charge, just like if you had two magnets together. And this will occur between metals and nonmetals because they're the only ones that have the greatest electronegativity difference to give us an ionic bonding. The closest to nonmetals we get was the HF example that we saw previously. But whenever we have metal and nonmetal, that's when we tend to get electronegativity differences of greater than 2. And so you can see here what happened is the sodium's electron actually gets transferred and given completely over to the chlorine. So now the sodium's lost its 1 electron. It's got a noble gas configuration when it's an ion. And the chlorine, since it has an extra electron, it has a noble gas configuration. Looking at that electron transfer, we can examine it using electron configuration and orbital diagrams. So if we look at the example of lithium fluoride. Lithium fluoride is a metal and a nonmetal. If you look at its configurations for lithium, I have a 1s2, 2s1. Fluorine is a 1s2, 2s2, 2p5. So you can see lithium has 1 extra electron above the noble gas configuration. Fluorine's missing 1 electron to get to the noble gas configuration. So if lithium gives up the 1 electron in the 2s orbital, gives it to the fluorine, lithium ends up as a 1s2, fluorine ends up as a 2p6. So now they've both obtained a noble gas configuration. And we can see that with the orbital diagrams. The red electron here, that's going to be given over to the fluorine. So now lithium has completely emptied its n equals 2 level. Fluorine has completely filled its n equal 2 level. And we can also draw that using what we call Lewis electron dot symbols. So each dot here, that represents 1 electron. So that'd be the 1 electron here. We draw the valence electrons as dots around the atoms. Fluorine, since it has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7, we draw 7 dots, 1, 2, 3, 4, 5, 6, 7. So all the 7 electrons here are drawn as dots around the fluorine, which means when this 1 electron gets transferred over, look, we don't draw any dots around the lithium. It doesn't have any valence electrons now. Fluorine has 8 dots around it. It has 8 valence electrons. And we're going to see these Lewis electron dot symbols a lot in the very near future when we start drawing our Lewis structures. But this is what each of the dot represents, is a valence electron. And so if we briefly look at the properties of our ionic compounds. Ionic compounds tend to be hard and rigid and brittle, with very high melting points. Most ionic compounds do not conduct electricity in their solid state. So if I just took salt, sodium chloride, from the container, it's not going to conduct electricity. Instead, if I dissolve it in liquid and make a solution, make it aqueous, then it can conduct electricity. Alternatively, I can heat it up really high and melt it, and then it can conduct electricity as well. And with ionic compounds, if you take a hammer and smash a crystal, it tends to break along kind of planes. So break along usually a fairly straight plane. And this happens when we hit it. It's actually just kind of moving all of the atoms that got hit over a little bit. And if you end up with two positive charges and two negative charges next to each other, that's when they want to repel each other and your crystal cracks. And then looking at the conductivity, if you just take straight salt as a solid form, no electricity. If you melt it, then you can get electricity flowing through the melted compound. Or easier way, just take your ionic compound and dissolve it in water. Then again, you can get electricity flowing, and we can see that the ionic compound is conductive. So one last property with our ionic compounds. Ionic compounds of like charges repel each other, and opposing charges attract. So within the ionic structure and crystal lattice, there's this balance between the attraction of the cation and the anion and the repulsion of the two cations. And the way they end up arranging themselves is a regular repeating pattern. And this is what we call a crystal lattice. So within the crystal lattice, there's a regular repeating pattern of positive, negative, positive, negative, positive, negative. And so now you guys should know a little bit more about ionic compounds, some properties of ionic compounds, and how the electron transfer actually works, looking at either your electron configuration, orbital diagrams, or now looking at the Lewis electron dot symbols.